everybody. Welcome to Synthetic Intelligence Forum Online. My name is Vic, and it's my pleasure to welcome Professor Sheila McIlraith to today's stream. Professor McIlraith is a professor in the Department of Computer Science at the University of Toronto, is a CFAR Canada AI chair as well at the Vector Institute, and also is affiliated as a research lead with the Schwartz-Riesman Institute. Professor McIlraith has a long and distinguished research career as a scientist, as a scholar, and is going to talk to us about a very interesting topic today associated with reinforcement learning. So without further ado, I'm going to welcome Professor McIlraith to the stream. Welcome, Professor McIlraith, and your slides are on, and feel free to take us away. Thank you.
Very good. Thank you, Vic. And it's a pleasure to be here. So thank you very much for the nice introduction. So what I want to talk about today is building taskable reinforcement learning agents, basically building agents, artificial intelligent agents that learn and adapt over time. And before I begin, I want to acknowledge my PhD student, Rodrigo Toro Acarta, whose work is what I'm talking about today. And he's done some of that work in conjunction with other colleagues and students, most notably Toran Klassen and Rick Villenzano, as well as Leon Ilanes. But many of these other students will I'll be referencing either throughout the talk or at the end of the talk. So how do we advise, instruct, task, and impart knowledge to our reinforcement learning agents? That's the question that I want to address today. And let me just break it down a little bit for you. It's fun to think about it in the context of a particular application. So I'm going to talk a little bit about, just to help you gain some intuitions. Think about having a robot in your home that you'd like to be able, who comes into your home that you buy off the shelf with some certain set of capabilities, but you'd like to be able to tell that robot what to do. You'd like to tell it how you like things done in your home. That's the intuition behind the class of problems that we're going to talk about today. And we're going to use reinforcement learning as the learning paradigm that we're going to use. For those who might not know about reinforcement learning, let me just give you a sort of a bird's eye view of how it works. The premise is that you have an artificial intelligent agent, the purple box on my screen, but here it would be a robot or a game playing program that doesn't know anything about the environment except that it has a set of actions that it can perform. So it performs an action in the environment, and the environment tells it what state it's in, and it also tells it whether it gets any reward, positive reward or negative reward. The agent continues to act, trial and error, trying to accumulate, to develop a policy, which is a mapping from its state to its action. So I'm in this state, I perform this action. I'm in this state, I perform this action to generate a policy that maximizes its expected cumulative reward. So it's really operating experimenting in the environment through trial and error, trying to maximize some reward that it garners when it performs an action. And that reward, the crux of the problem that I want to talk about today, is that the reward that we specify, this R of S, that maps a state to some sort of a scalar value, or it maps a state, the action that it performed, and the subsequent state that it ended up in, that triple, into some sort of scalar reward. And it could be plus 100 or minus 60 or plus 1,000 and so on. And that's a very narrow lens by which we can actually specify what we want. That's the only way we can specify what we want an agent to do. Juxtapose that with what you and I might think of sitting on our sofa, being able to tell our robot what we want it to do. So there's a big gulf between these two things. And what happens right now is that our poor graduate students usually are stuck somehow trying to figure out how to take some very complicated behavior that we want our agent to perform and shoehorning it into, or programming it into, this function, this R of S function, of R of SAS prime function, in order to tell our agent what we want it to do, in order to task our agent. So you don't need a PhD to raise a child, to teach a child how to behave, and you shouldn't need a PhD to task an RL agent either. And that's sort of the premise behind some of what I'm going to talk about today. I wanted to pause for a minute and actually talk to you more generally about real-world reinforcement learning. There's a very interesting paper by Gabriel Dulac-Arnaud and some of his colleagues on some of the challenges that really face reinforcement learning. And for anybody who's in the real world, and for anybody who's interested in this, I'd recommend that you take a look at that paper. It's an easy read. He's got 9 high-level challenges, but certainly focused among those challenges are 2 challenges that I'm going to talk about today: reward specification. As I've alluded to, it's really hard to define reward functions for complex tasks. And the second problem is sample efficiency. Reinforcement learning agents might require billions of interactions with the environment to learn good policies. And for those of you who've seen some of the amazing things that we've done with reinforcement learning, behind the scenes, what you don't necessarily see unless you're trying to build these systems is an awareness that it takes millions and billions of trials and error for the agent to learn how to act at a high level of performance. Often because rewards are sparse, because for every action it doesn't necessarily get a reward. And so that creates a real challenge for us for building reinforcement learning systems, whether our agent is actually interacting with the world or whether it's interacting with some sort of a simulator that simulates the environment that the agent is eventually going to act in. So let's get back to our task at hand, which is, imagine we've got a robot that's just come into our home. We'd like to be able to advise, task, and instruct it. And just to sort of ground that, here are a couple of examples of things that I might like to say to my reinforcement learning agent. Run the dishwasher when it's full or when dishes are needed for the next meal. Make sure the bath temperature is between 38 degrees Celsius and 43 degrees Celsius immediately before letting someone enter the bathtub. That would be a good property for a healthcare assistant robot in a home, or perhaps for somebody who's babysitting your children. Do not vacuum while someone is in the house is sleeping. What's interesting about these goals and preferences is that they are temporally extended. They don't just talk about the state and the current state, but they talk about an evolution, and they're also conditional. I'm conducting a little reinforcement learning experiment in my home with my children. It seems to be very hard to learn, but here's my preference. When getting ice cream, please always open the freezer, take out the ice cream, serve yourself, put the ice cream back in the freezer, and close the freezer door. If you perform that task to completion, you get a reward. If you only perform half of that task, for example, if you take the ice cream out, serve yourself, but leave the ice cream on the counter and leave the freezer door open, you're going to get a very high negative reward. So, or you're going to get no reward at all. So what I want to exemplify by this example is really that the reward is shoehorning that into a mapping from state to action or state to a scalar value is very hard, because what we actually want the agent to do is much more complicated than that. So what I'm going to talk about today is a way of encoding this in a formal language called linear temporal logic. Some of you who are technologists may be familiar with this language. If not, don't worry about it. There's just a high-level bit that you need to understand. This language has been used for years and years for automated program synthesis, but also for formal verification of systems. It's a formal logical language with a set of modalities like next, weak next, until, eventually, always, that allow us to talk about properties of evolutions, properties of the evolution of an agent over time. They can be interpreted over finite or infinite traces. And importantly, and I'd like you to remember this, they can be transformed into a finite state automaton. So I'll return to that in a minute. Here are a couple of examples just to ground it for you. Again, we had these temporal modalities called always, so, and eventually, and next, and until. So do not vacuum while someone is sleeping could be represented in linear temporal logic as always, not vacuum and sleeping. So vacuum and sleeping can never co-occur in a state. Or my ice cream example could similarly be represented as always. If you're getting ice cream, then it implies that eventually open the freezer, and after that, next, remove the ice cream from the freezer. After that, next, serve the ice cream, and so on. So it's a fairly straightforward language that captures these representations. So how do we communicate this sort of thing to our RL agent? And so let me just look at the motivation. So again, remember, we wanted to talk about reward specification, how I'm going to specify those complex rewards, and also how I'm going to learn in a sample efficient manner. And to illustrate some of what I'm going to talk about in the rest of the talk, I'm going to use this very, very simple running example. It's a grid world, an office world environment, where I have a number of different things in the environment. The little purple triangle is the agent who's going to be moving around in the environment. I have a bunch of different locations, A, B, C, and D. I have 2 coffee stations represented by the coffee mugs, a mail room represented by the envelope, and then a little thing called O, which is the office. And the stars are furniture, which I don't want to bump into or damage in any way. So the task that I might like to perform, just for the sake of this example, is to patrol around from A to B to C to D and not touch any of the furniture. So actually, this is a toy problem, but it challenges state-of-the-art RL. So the important observation is the following, and the observation that is at the crux of, I think, this work that I want to talk to you about today, or at least one element of it, is that somebody always has to program the reward. And this is true for anything that you do in reinforcement learning. And it's a dirty little secret in some ways, because if you think about this model of learning by trial and error, for us, we're pre-programmed. I feel happy when it's sunny out. I feel, I get pleasure when I eat ice cream. I get pain after I exercise. But I also feel happy because I have endorphins that make me feel happy. So, but for any sort of artificial intelligent agent, somebody has to write something. Again, usually one of our poor graduate students who's going to write a bunch of Python code or something else to define the reward function. Even if the agent, the robot, is interacting with the real world, that code still has to be written by somebody. And so the simple, and of course, normally in reinforcement learning, it's treated like a black box. So the agent moves, it expresses its state, and the black box tells it what reward it gets, and so on. It moves around and it's getting all these zeros. So the simple idea, and something that I want you to remember, is the following. What we're going to do is why not give that reward function, the code for that reward function, to our reinforcement learning agent, expose it, and also expose the structure of that reward function so that the reinforcement learning agent can learn more quickly. It's a simple idea, but as you'll see over the course of this talk, it's going to prove to be a very effective mechanism for doing reinforcement learning much more sample efficiently. So we'll back to our running example. We've got our Python code there, and we're going to expose it. And now we're going to show effectively what we're doing in the context of reinforcement learning is that we're decoupling the transition and the reward function, and we're actually giving that reward function to the agent. So in the rest of the talk, I'm going to talk to you about how we're going to represent that reward function in terms of something called a reward machine, how we're going to exploit that structure in learning, some experiments, and some other interesting work. So here we go. So reward machines. So we're going to define, remember I told you we want to write our function and we're going to expose it. And we could do it in Python code, but what we're going to do instead is we're going to use a form of finite state automata over a set of vocabulary that we're going to provide that is in the case here where we're doing something that is human specified. We're going to use a vocabulary that isn't computer interpretable and that you and I might use if we wanted to define a reward function. Note that if you're not interested in human specification, let me just say that all of the work that I'm talking about today, we can also learn these things. We can learn a vocabulary and we can learn these structures. And I'll talk a little bit more about that at the end. But for now, we're going to assume that we have a vocabulary, and you can see it at the bottom: coffee cups and coffee stations and mail rooms and offices and furniture in these different locations. So our reward machine is going to be a finite state automata structure that's going to represent our reward function for us. So here we go. So the reward machine is comprised of a finite set of states. So those are the states of our finite state automaton, an initial state, U0 here, and a set of transitions that take you from one state of the reward machine to another state of the reward machine. And those transitions are labeled by two things. They're going to be labeled by a logical guard, or a condition that must be true in order for that transition to occur, and also by a reward function or a constant. So in the case of the transition from U0 to U1, we see that we have a logical condition, which is just that A is true, and a reward that we get for transitioning from U0 to U1, which happens to be 0. And you'll note here, again, as we saw with that patrolling task, we want to go from A to B to C to D, and we only want to get reward when we finish that loop. So we only get a reward of 1 when we've gone to D and transition and finish. So for those of you who do know something about automata, you'll note that a reward machine is like a type of Mealy machine over the finite alphabet, which is all combinations of permutations of the way the world can be according to those propositions. So let's just see it in action. Now, if our agent moves around, it goes through a state and it gets reward, but it's also transitioning, skip a few, 99, 100. It's also transitioning, as it's transitioning through the environment, it's also transitioning through this reward machine. And as it gets to the bottom, it's gone through A, it's gone to B, it's gone to C, it's in state U3. And now when it goes to D, it actually gets this reward of 1 finally. The finite state automaton is this function that gives a Markovian decomposition of what's going on in the environment, and it allows us to give a reward of 1 at the appropriate stage. And it also exposes some of the structure of our function in a nice way. So we can also define, in addition to that patrolling task in the office environment, I could also define a reward machine for delivering coffee to the office while avoiding furniture. And you'll see that there are 2 transitions. I stay in my start state until I get to a coffee station, and recall there was more than 1 coffee station. If I coffee station and I haven't hit any furniture, if I satisfy that, then I get a reward of 0, but I move to U1. And if I then subsequently go to the office while still not hitting furniture, then I'm going to have delivered that coffee and I'll get a reward of 1. If for any reason I hit the furniture at any point in time, either before or after I've been to the coffee station, then I'm going to fall into this sync state where in perpetuity I'm going to get a reward of 0 because I have not been able to achieve the task that it was described with a reward of 0, while avoiding while avoiding the furniture. Similarly, if I have different ways of doing things, deliver coffee and mail to the office, I might deliver the coffee and then the mail, or I might deliver the mail and then the coffee, and those different types of pathways can also be represented within my reward machine. So I've told you how I'm going to specify my reward function in a structured form that provides a decomposition of that task and that provides bookkeeping. Now the question is, how are we going to exploit that reward machine structure in learning? And remember, the reason, the hypothesis for this is, the premise behind this is that we think that by exposing that structure, we're going to be able to learn more quickly. So let's see how we do that. So what I'm going to talk about just is 5 different approaches. 3 are sort of baselines that we created, and the last 2, numbers 4 and 5, are particular techniques that we developed that really exploit reward machine structure. 1, 2, and 3 also exploit structure, but they're not as were developed by us, but they're not as good as the ones that I'll tell you in 4 and 5. So our first baseline is just to do basically a cross product. So the reward machine, and in order to learn why this is worthwhile to do, I wanted to make the observation that a reward machine may define a non-Markovian reward function. So remember that when you saw that reward function, R of S or R of SA S prime, it was a mapping of the current state to, or the state action state triple to a scalar. But sometimes, like my ice cream example, for example, the reward is predicated on things you've done in the past, and that makes it non-Markovian. It's not only dependent on the current state. So just to illustrate that here, if my little agent is at D, but it was actually in U, it got to D via U1. So for example, it had gone to A, and then it went over here and went immediately to D, so it's in U1. Then it's going to tell the reward function that it was in U1 and now it went to D, and the reward function is going to tell it that it gets a reward of 0. If it was in U3 and it tells it it's at D, and it will have gotten to U3 if it's gone from A to B to C, and it then progresses to D. then it's going to get a reward of 1. So same movement, moving from the position to the left into D, but the reward is different because the reward depends on the history. The reward is non-Markovian, and that's captured by our state. So in order to do that, our first baseline is simply to do to include the reward machine state as part of the agent state representation, and then to use Q-learning on the resultant Markov decision process. Q-learning is one of several approaches to reinforcement learning. The second baseline that I'm going to show you to compare our results is to use hierarchical reinforcement learning. A hierarchical reinforcement learning is a form of reinforcement learning where the reinforcement learning agent it learns a set of different options or policies for different macro actions, if you will. And in this context, what we're going to do is we're going to learn one option policy for each proposition mentioned in the reward machine. So we're going to learn a policy for getting to A, a policy for getting to B, a policy for getting to C, and a policy for getting to D. And those are going to be referred to as pi A, pi B, pi C, and pi D. So my agent's going to operate in the environment to learn each of those policies. It's going to optimize each of those policies. And then it's going to construct a meta controller that decides how to combine those policies together in order to do reinforcement learning. And this is a very effective technique that's already used in practice today for decomposing gnarly problems, and it's referred to as HRL. So that's going to be one of our baselines, and we're going to learn a meta controller that uses these individual policies that we've learned. Our third baseline is just a variant on that, which is the simple observation that if we have this reward machine that's sort of telling us we're at U0 or U1 or U2, why not use it in order to help inform the meta controller about what to do? And so our third baseline is something that actually does that. So we know that if we're at U0, we should be using pi A because we need to get to A before we do anything else. When we're at U1, we know that we need to use pi B because we need to get to pi B. So we're going to use that structure to help the meta controller learn what to do in each of those environments and each of this, whatever state it's in. And so that's a big help to the system, as you will see. The problem with HRL, just as a foreshadowing of some of the experimental results that I'm going to show you, is the following. Because hierarchical reinforcement learning decomposes the problem into a bunch of different subproblems, each subproblem is actually solved myopically. It's going to find the best policy to get to A, the best policy to get to B, the best policy to get to C, and the best policy to get to D. The problem is when you combine those together, the aggregate may not be optimal, even though each of those policies individually is locally optimal. And a good way to illustrate that is the following. So if I optimize, here's the optimal policy. The optimal policy for solving this coffee delivery problem, where I go to a coffee station and then I deliver the coffee to the office, is to go for the agent to start at A, to go up here and to get the coffee, go to this coffee station, and then which takes 10 steps, and then to take the 3 additional steps to go to deliver it to the office. The problem is, this other coffee station is closer. And so the optimal policy for pi of A will tell the agent to go to this very close this closer coffee station. But unfortunately, what then happens subsequently is that it takes a very long time for that agent to get to the office. So there's no look ahead with hierarchical reinforcement learning. And each of those policies is decomposed and constructed on its own without any look ahead. And that's something that you'll see in our results. So the fourth algorithm that I want to show you, which is our big contribution, is this notion of Q learning with reward machines. So this notion that we're going to give the reward function to our reinforcement learning agent, but in a very contentful way. And let me tell you how this works. So we're going to learn one policy, one Q value function per state in the reward machine. So one for Q0, one for Q1, one for Q2, and one for Q3. And just foreshadowing, at the very end of this talk, we have a different type of algorithm that we've just developed that is an update of QRM that I'll mention at the very end. But for the purposes of the talk here, this is an easy way to understand what's going on. So one for each. We're going to select actions using the policy of the current reward machine state. And then, so when U0, we're going to use Q0. When we're in U1, we're going to use Q1, U2, and so on. And then what we're going to use, and this is the interesting thing, in order to improve sample efficiency, we're going to reuse our experience to update all the Q value functions on every transition via off-policy reinforcement learning. What we're actually doing is a form of counterfactual reasoning. So what I'm doing is, if I'm at U0 and I have some experience, I'm going to update my Q0 policy that I'm learning. But I'm also going to say, if I had this experience and I was in U1, how would it have affected Q1? And if I was in U2, how would it have affected Q2? So I'm going to be able to reuse those experiences for each of these sort of sub-policies that I'm learning. And that causes us to learn much more quickly, as you'll see. So here's QRM in action, just to ground what I just told you. So we're going to select an action according to the current reward machine state. So here I am, my little purple triangle right beside D, but I'm in U0. I haven't gone anywhere. I just got plopped into the office, and I happen to be where I'm located right now. I'm in the initial state, and I move. I'm going to update my Q value based on my action. So for Q, for when I move to D from that previous position, if I'm in U0, I get a reward of 0, and I'm going to update my Q value, which is a mapping from state and state and action to some value, and it's going to be my current reward plus the discounted future return that I expect to get. So which will be the maximum of optimizing my choices for future state, for future reward at that state. But I'm also going to counterfactually update everything else. So I'm going to update Q1. If I'd been in Q1 instead of in Q0, what would have happened? I would have updated my Q1, my Q1 value by the reward that I got, which is 0, plus the discounted future reward, which will, and since I'm still in Q1, it's still going to be Q1. If I was in U2 and I performed that action, same thing. I'm going to transition back to Q2. I'm going to get the reward plus the maximum of the future reward I expect to get at Q2. But if I'm at Q3, or if I'm in I was at U3, then, and I performed that action, then the situation would have been different. I actually would have gotten a reward of 1, and I also would have transitioned to U0. So my update is going to be for Q3 is going to be 1 plus the max of the expected reward future reward I'll get at Q0, which was different from the others were staying in the same place, whereas this one actually allowed me to transition. So note that. So that was a form of counterfactual reasoning, because in addition to just updating Q0, I was also able to sort of think in my head and imagine what would have happened if I'd been in one of these other states. And that allows us to learn much more quickly. So I've told you about 1, 2, 3, and 4. The last approach I want to tell you about is the use of reward shaping, QRM with reward shaping. And this was something we did a little bit after our initial work on QRM. So the idea, this text is here for those who want to read it, and I'll read some of it, but let me just tell you about the idea of reward shaping. A lot of rewards are sparse. You'll notice that even in our little patrolling system, or even when we were delivering coffee, a lot of the time the agent is moving around the world and getting a reward of 0. And that doesn't really help it or direct it to learn very easily. So the idea behind reward shaping, and I seem to think a lot about food, but I think about a cookie, and you have some sort of a cookie, and instead of getting all of the cookie when you get to your final destination, I'm going to take that cookie, sort of like Hansel and Gretel, and leave little cookie crumbs, break it up to relieve little cookie crumbs along the way. But I still only have 1 cookie, so the sum is always the same, but I've broken it up in some way. And reward shaping allows us to break up the reward and distribute the reward over the states in a manner using a form of potential function that's going to preserve the optimal policy. So reward shaping always preserves, is a rewriting of this reward function by adding and subtracting some reward according to a potential function, but that most importantly allows us to learn optimal policies more quickly, and by giving us more signal back on every step rather than having this sparse signal, but it guarantees that the found policies are still optimal with respect to the original reward function. Very important. So that was our last task. And here's just an example of what a reward function with reward shaping might look like. And what we actually did was we just did, for those of you who are familiar with the details of some of the details of reinforcement learning, we just did value iteration over that reward machine structure in order to add these red parts. We're adding a little bit of reward here, we're subtracting some reward here, and that provides more localized incentive or disincentive to the reinforcement learning agent in order for them to learn a little bit more quickly. So that's the idea behind reward shaping, and we added that on top of our QRM algorithm to see how well it worked. So a nice thing about QRM and QRM with reward shaping, and this is a theorem, which I'm just stating informally here, which is that QRM converges to the optimal policy in the limit, as does QRM with reward shaping. And that's in the tabular case. More generally, any sort of guarantees that are given by Q learning are preserved with our Q learning algorithm. And what we'll see is that when we do tabular Q learning, there is a guarantee that if you have enough samples, if you have enough experiences, that you'll eventually converge to an optimal policy. Whereas in a deep case, in deep learning, deep reinforcement learning, where we're doing function approximation, we lose that guarantee, unfortunately. So I've told you about reward machines, how we're going to specify these rich structures. And I've also told you how we're going to exploit them. Let's see how they actually learn in practice. So here's some experiments. So we tested on two simple domains with discrete actions and state spaces, the office domain that you saw before, and also a Minecraft-like domain with 10 tasks. Those were discrete tabular domains. And we also experimented with deep reinforcement learning in an environment called the water world environment. And we tested all 5 of the approaches that we've developed. Some of them guarantee optimality in the tabular case, like Q learning, and QRM and QRM with reward shaping. And of course, the HRL, the hierarchical reinforcement learning algorithms don't. And then some of them use decomposition while others don't. And so those are different properties that will be interesting to see how well they do. So here's our office world domain. We had 4 different tasks, 30 independent trials. We're going to look at this graph that's on the right that's going to provide our results. On the x-axis is the number of training steps, which goes up to 50,000. And on the y-axis, the vertical axis, is the normalized discounted reward. So we've normalized all the reward that we might get to 1, so that we have an even playing field in terms of the reward. And of course, 1 is optimal. So we're going to compare 4 different approaches: Q learning, hierarchical reinforcement learning where we were doing the pruning with the reward machines, and our algorithm QRM. And let's see how it works. So as you can see, QRM, our algorithm, very quickly converged to the optimal solution. So again, 10,000 trials, just between over 10,000 training steps, which is in contrast to Q learning without the reward machine, which it was a conventional, algorithm that is being used, which never converges to the optimal policy in the time that it has. But of course, remember, Q learning is guaranteed to converge in the limit, which speaks to this issue, of sample efficiency, which is eventually, if I extend this x-axis in perpetuity, eventually that blue line will get to the top. What we also see between our 2 hierarchical reinforcement learning algorithms is that the one that used the reward machine pruning did better, and it looks like it sort of reached this asymptotic behavior. But remember, because it was, it often will lose the optimal policy, the ability to find the optimal policy. We see that here, where the reward is never going to converge to the optimal just because it did this myopic localization of these different policies. We also did 10 tasks over 10 random maps in this is a Minecraft style environment. So we've got Luigi, and Luigi can get wood, and he can get metal, and he can make various things in his environment. Again, we have the same X and Y axis here. This is the X axis, the number of training steps is up to 10 to the 6th. The y-axis, the vertical axis, is the normalized discounted reward again. And we have the same 4 algorithms that we are testing. And the results, again, show that our approach, the red approach, converges to optimal, does it very quickly. And for those of you who don't have very good eyesight, or maybe you're looking at the screen on it, you're thinking, where's Q learning? It's flatlined. It's down here. And again, I will point out that Q learning is guaranteed to converge to the optimal policy, but because these are sparse reward environments, it's really hard for it to even get, it's not doing anything even after 10 to the 6th experiences, but it will eventually converge to 1. And it just speaks to how important it is to exploit that structure and the effectiveness of our techniques. Similarly, we did work with function approximation in a deep learning environment. We replaced Q learning by double DQN, DDQN with prioritized experience replay. Again, when we do function approximation, we lose those guarantees of optimality, but we still retain our ability to decompose. The environment that we worked in is this environment called the water world environment. It's like billiards, so or pool. So the agent is this little white ball, and all of these, the colored balls are moving in the environment, bouncing off of the walls. And what the agent has to learn, what it's tasked to do, are simple tasks like hit 2 purple balls and followed by a green ball, or never hit a yellow ball, or always hit 2 blue balls before you hit a pink ball, and so on. So again, we'll look at our results with the same normalized reward at the top, and the same on the y-axis, or on the x-axis, the same number of training steps, again up to 10 to the 6th. And what we'll see again very impressively is that our DQRM, our QRM algorithm using deep reinforcement learning, again shows far superior performance. For the time that we had, we didn't reach optimality, but we were doing much, much better than hierarchical reinforcement learning with reward machines, hierarchical reinforcement learning, and again, double DQN, which these experiments are a little bit old now, they're a couple of years old, which in machine learning life is a long time, but it still was doing far better than what was the state of the art then. And we've got updated experiments that I just didn't create graphs for that similarly show that we're really doing far better than the state of the art, and should always do far better than the state of the art because of our exploitation of these reward function structures. So we did some experiments with reward shaping, and we did them post hoc. I've got the examples in the 2 tabular domains and the water world domains. The black line is QRM with reward shaping, the red line is QRM, and of course the blue is just regular Q learning. And we were doing, the reward shaping seemed to help in the tabular domains, but not help so much, or actually be a little bit of a hindrance in the continuous domain. And we have some insights regarding that, but nothing that I can talk about afterwards, nothing profound. So creating reward machines. So hopefully I've convinced you that using reward machines and giving function structure to the reinforcement learning agent is really an effective way to get things done. And that it improves sample efficiency and allows us to actually solve problems that we might not have otherwise been able to solve. But a sticky question is thinking about that guy who's sitting on the sofa talking to his robot in his home. How do we actually create these reward functions? So I just wanted to talk very quickly about 3 different ways that you could do it. And the one obvious way is directly, that you could actually write the reward function. Another way is that you could generate it, and another way via some high levels from some other high level specification, and another way is that you can learn it. And I'm going to just dive down into each of those three different ways: specify, generate, or learn, very quickly. So one type of reward specification does not fit all. For those of you who work in industry, you know we spend a lot of time in industry designing sort of outward-facing or user-facing specification. And perhaps the most obvious way we aspire to here is that we'd like to be able to talk to our robot. So interestingly, we might be able to use we might aspire to use natural language, or we might aspire to use some sort of other formal language. We noticed that reward machines are automata, and it's actually interesting to note that without any further work, we can specify reward-worthy behavior in any formal language that is translatable to a finite state automata. On the right on this slide is a picture of Noam Chomsky. Some of you may know him for his political views. Others may know him, and we know him in computer science, of course, because he defined Chomsky hierarchy, this beautiful hierarchy of languages, and that gets us all the way up to unrestricted languages and Turing machines. And depending upon the expressive power of your language, those languages can be represented by finite state automata, by push-down automata that have some memory, or by linear bounded automata, and so on. So because reward machines are a form of Mealy machine and they're a form of finite state machine, we can capture any regular language in a reward machine. And that's a beautiful idea, because it means that we could specify in any language of our choice that is translatable into a deterministic finite state automata, and then automatically translated to a reward machine. And the nice thing about that is that the reward machine, that automata structure, becomes a normal form representation. So we can build, the algorithms that we built, or maybe somebody else will build a better algorithm that will use that reward machine structure to support learning. And we don't have to build a different algorithm for every different type of specification language that we might like to use. So that's a real beauty of using this formal language and this sort of normal form structure. So remember this. And again, you'll notice on the right, when I talked to you at the beginning about linear temporal logic, those very rich, and I also noted that linear temporal logic can be compiled into automata. A subset of linear temporal logic, a very rich subset of linear temporal logic interpreted over infinite traces, and all of linear temporal logic interpreted over finite traces can be compiled into deterministic finite state automata, as we've shown in a subsequent paper. And so we can use it, we can specify those as reward machines. So very nice. The second thing we can do is actually generate a reward machine using a symbolic planner. And I'm not going to talk to you about that today, but just a heads up, if you're interested, there are some citations to some papers. Some other work that we did was just to give a final state goal to a symbolic planner that had a very high level abstract notion of how the world works. And it could generate plans for how to achieve goals at a very high symbolic level. And then create a reward machine, and then use that with hierarchical reinforcement learning in order to do the type of learning that we were doing here and benefiting using hierarchical reinforcement learning. And the beauty of this is that rather than generate complex instructions, a symbolic planner is generating those complex instructions for you, creating those waypoints, if you will, that the reward machine provides, and then automatically constructing that reward machine. So that's a second way of doing it. And the third way of doing it is to actually learn reward machines. And so what I wanted to do is just give you a shout out to some interesting work that we did in learning reward machines, and to tell you how hard it is, and to tell you some of the progress that we made. So, and I'm almost done my talk, so I know we're getting close to the time when I should be stopping, but this is sort of an interesting problem. So if you look at the Dulac-Arnold paper, they will tell you that one of the challenges to reinforcement learning in practice, and one of the challenges that should make sense to all of you, is that we don't always have full observability of our environment. Maybe we do when we're working with a nuclear power plant or some sort of controlled environment where we have where we're trying to control some device like a photocopier. But for agents that are acting in the world at any one click of the clock, they don't have full knowledge of the environment. They only have a view of the environment. And so this partial observability can be problematic. And so just to illustrate that, I wanted to show you this very simple example of a toy example, but it's a very evocative example. So imagine I'm this little purple agent, and there's a corridor, this T-shaped corridor, and there are 3 rooms: a yellow room, a blue room, and a pink room, or red. I'll call it red, a red room. And in the yellow room, there's a button. And when I press the button, a cookie magically appears in either the blue room or the red room. But I, as the agent, cannot see this because I can only see what's in the environment that I'm in. So I'm in the corridor, I can only see the corridor. And when I'm in the room, I can see what's in the room. But when I'm not in the room, I can't see what's in the room. So the problem here is that I want the agent to learn that it needs to push the button. And once it's pushed the button, it needs to find the cookie in one or the other of the rooms and eat it. It gets some reward for eating that cookie, and its objective is to maximize its cumulative reward. So to eat as many cookies as it can, and to learn a policy, a mapping from state to action that will tell it what to do. And to just tell you how pronounced that problem is, imagine being here, and the agent has no recollection of what it's done in the past, and yet it needs to be able to remember what it's done in the past in order to decide how to act. Because if it's just starting out, then it needs to go up to the yellow room and press the button. If it's already pressed the button and it's back here, then it needs to go to one or the other of the rooms to look for the cookie. If it's gone to one of the rooms and found the cookie and eaten the cookie, then it's back here and it needs to go back and press the button again. But if it's gone to a room, either of the rooms, and hasn't found the cookie, then it should learn that the right thing to do is to go to the other room, and because it will find the cookie there, and it will learn that through experience. Very, very hard. And of course, it needs this external memory somehow in order to be able to do this. But we did this by learning a reward machine with discrete optimization. And we used discrete optimization and taboo search to do this. It sounds like a really toy problem, but state-of-the-art reinforcement learning algorithms at the time we did this, which was 2019, like A3C, PPO, ACER, with LSTMs could not solve this problem. And so we were able to learn this reward machine. And the nice thing about it, just as a further shout out, is that it's actually quite interpretable. I'll leave it to you to stare at it, but when you're starting out, if you go to the yellow room and you press the button, then you get to U1. If you go to the pink room and you eat a cookie, you go to U2, and so on. If you go to U2 and you get the cookie, then you get a reward of 1 and you go back to the start, and so on and so forth. So we learned this very nice finite state automaton through interacting with the environment with partial observability. And we did great. All of these state-of-the-art techniques, again, training steps on the y-axis, reward on the x-axis, and reward on the vertical y-axis. The state-of-the-art techniques were not able to solve this problem. They're flatlined, these deep reinforcement learning algorithms, whereas using LRM, learning reward machines, with either deep QRM or even with deep reinforcement learning without using the DQRM, we were able to do very well. And the green at the top is the optimal behavior. So we were very quickly able to learn a structure that helped us to learn how to solve these problems very quickly. So I'm done. I'm just going to recap quickly, just to send you the message again, which is that we were interested in understanding how to advise, instruct, or task, impart knowledge to our reinforcement learning agent. I think that's our big challenge. And again, because the way that we have to communicate with these agents right now is through that RS maps into the real numbers, very difficult. So we wanted to, and one of the things we wanted to understand was whether exploiting the alphabet and the structure of language could help our reinforcement learning agent learn and think. And we showed that it actually did. The key insight was to reveal the reward function to the agent. And we created reward machines. We created this QRM algorithm, a QRM algorithm with reward shaping. We are able to translate reward machines from other languages in any language that is expressible in an automaton, including that very nice linear temporal logic language that I showed you at the outset, but also any regular language with if, then, else, and while loops that is typical of most procedural programming languages. We're also able to learn reward machines, and we're also able to task them. We get great results in discrete domains, and in continuous domains. We can construct the reward machines from a diversity of formal languages, and we can generate them using symbolic planners, and we can learn them in partially observable environments to solve really hard problems. We've got lots of code and papers that are available in these slides that are listed here. We've got some other related work that I didn't talk about, this earlier work in this area. And we've also got our latest work, and just a little bit of a shout out for anybody who does want to use reward machines. We've actually extended or done a variant of QRM, which is called CRM, counterfactual reward machines, where rather than learning individual policies, we're learning one big policy, and we're just sort of contextually deciding which part of that big policy we're going to learn. And our hypothesis in doing this was that might make, rather than separating out these policies into the Q0 policy and the Q1 policy, they're still indexed with respect to Q1 and Q0, but they're all within one big policy, which will help us hopefully with generalization. And then we've done some other nice work that is peripherally related to learning instructions in a structured form using linear temporal logic that's currently under review. But if you do want to experiment with this and you want to use the code, I encourage you to go to Rodrigo's webpage and to look at this particular work. So again, acknowledgements to Rodrigo Toro-Accarda, Torin Klassen, Rick Valenzano, who is now who was at University of Toronto, then Element AI. He's now just starting a position at Ryerson. To my other graduate students who've worked on this, a big thanks. So that's it. I'm going to, I guess, hand it over to you guys again.
Yes, thank you, Sheila. This is a great talk. I very much appreciate it. So I have just a quick comment and just two questions, and I'm going to put them all out there, and you can definitely engage with them as the way you see fit. There's also great questions in the chat. We won't have time to go through all of them, but happy to share a couple of them. So just a quick comment. I looked very interestingly at your algorithm, Sheila, in the QRM, where you have this notion of retrospective updates, where when you go to future states, you can actually update the hind states. And it kind of reminded me of the work on eligibility traces in TD lambda learning and temporal difference learning. That was just a comment, brought back some interesting thoughts there.
Right.
But two quick comments I want to make is, so I looked very interestingly at, Sheila, some of your, on the paper that you have, I've kind of put that on the screen and I've highlighted that in that paper, and you mentioned to it that you use double DQN, and I like double DQN as well because it helps to minimize the overestimation when it uses the Bellman equations max operator, and so that's great. But also in terms of future work, and I know you talked about some of the other experimental results you've created, this notion of the dueling network architectures where you have one target network and then that periodically syncs with the trained network to stabilize some of the training and to improve some of the convergence. Also this notion of distributional perspective. So I was interested to see that now that you're actually exposing the turning the black box into a glass box, if you will, Sheila, of how those rewards are calculated, perhaps an approach that does categorical learning or distributional learning, where it's not mapping a state and an action to a scalar, but a state and an action to a distribution. Would that in some way benefit from your QRM approach? So just things, I think just interesting ideas. The second topic I wanted to discuss was the notion of...
If I could just say one thing with respect to this. So the reward, if you look at our original work, but when we formalized the reward machines, where the example that I used was actually a simple reward machine, but the reward doesn't need to be a scalar. It could be any arbitrary function. To your point, exactly, this same formalism works with any sort of reward function, not just a scalar value. So we can map that state rather than map into an R. We can map into another whole function. And that I think speaks to your idea very nicely. Yeah.
Yes, and I also found it interesting that when in your office world, you go from room to room, the actual underlying transition, the underlying reward probabilities might change as well. And that's why HRM shows some promise, but your approach even takes it to that next level. The other topic, Sheila, I wanted to talk about for future work perhaps would be this notion of multi-agent reinforcement learning, where I wonder if Q learning with nearest neighbors or mean field approximation, even if we were to actually expose the reward function to those multi-agent reinforcement learning type scenarios. We know with independent Q learning, some of the convergence guarantees, because then of course the actions of one actor changes the stationarity of the probabilities. But if we use something like, let's say, neighborhood Q learning or mean field approximation, I'd be very interested to see how this reward machine logic added on top of that, whether that accelerates the speech to convergence, whether it improves numerical stability. So if you're looking for collaborators, all I'm saying is there's plenty of interesting ideas that perhaps we could look at together as well.
Yeah, that's right. There are lots of interesting problems here, and also some questions. If you think about robots working together, they can do sort of the Star Trek Vulcan mind meld. They could arguably share their reward functions with each other, and I think some people would say that's cheating. And certainly if you're interacting with a human, you can't share your reward function. It's hard to sort of figure out what exactly it is that the human being is wanting. But certainly between interacting agents that are computer programs, effectively, the notion of actually being able to share their reward functions makes perfect sense, for building applications, certainly. And interesting to not do that and to see the contrast in other environments. Yeah.
So this is an interesting question in the chat, Sheila, I'd like to ask, which is that what's the logic behind giving the reward function, exposing it after the actual reward is issued? Could that reward function not be given even in an intermediary step before the actual reward is given in a multi-step process?
So the reward is, again, it's all code. I guess maybe the illustration was leading us astray a little bit, but the idea is that the learning algorithm has that reward. So but it's still interacting with the environment. So the environment is not it. And again, the environment could be a simulator or it could be the real world. And it's just the case that what the agent doesn't know is not just a reinforcement agent not only does not know its reward in a classical sense, but it also doesn't know how the environment behaves. It has no model of the environment. So it actually has to act in the environment, get that state, get her state returned, and then it assesses the reward in the context of that state that is the result of performing the action in the environment. So it does. I'm not sure whether so that's why you can't do it in advance.
Okay.
I'm understanding the question correctly.
Sure. And Sheila, maybe I can ask the last question here in the interest of time. So the question is that, it's fascinating when you started your talk, you said, hey, look, one of the things that is sort of almost sacrosanct in reinforcement learning is you don't know the transition probabilities and you don't know the reward function because, you don't have full visibility into the MDP. Otherwise, it'll be more of a dynamic programming problem than let's say, an RL type problem. And now we're actually sharing the reward function. Is there similar argument to be made, for example, to say that perhaps we now also start sharing the underlying transition function as well? And then do we say that we're back to sort of the full MDP dynamic programming world, or is it the argument that rewards, because somebody has to specify them, it is something we could explicate and pass out to the agent? Meanwhile, transition probabilities are inherently stochastic and they're governed by all kinds of unknowables that are inherently unknowables.
I'm a pragmatist. So yes to everything you said. I think there are many different interesting trajectories to go down. And if you're solving a problem, my opinion is bring everything to bear to bear that you can. I mean, we have controllers that are controlling our nuclear power plants and thankfully doing a very good job at it. We are sending spaceships to Mars, and we're flying drones on Mars and doing all sorts of things. without, many of them without using any form of machine learning. We're building models, we're relying on physics. And of course, and there are many tasks where those models of the environment work very well, where we're able to model the environment. I think where we're seeing reinforcement learning really going to hold a lot of promise is where the dynamics are so complex that they're not easily modeled or not understood, or where we want to perform something in different environments and where we want to use generalization, basically where the model is not sufficient, where we can't do that modeling. But there is this intermediary where we can do some modeling, and that may help us learn more quickly or give us some heuristics towards what we might try to do, what we might try to explore. And so I think there's a whole continuum of things that are interesting to try within that space in order to solve problems. And again, to address this important fundamental problem, which is one of sample complexity. When we're many of the tasks that we're dealing with now are in simulated environments where we can do 10 to the 6th experiences. But if you're a robot in your grandmother's house, you're not going to do 10 to the 6th experiments on her to figure out what it is that she wants. And we really do need to find other ways to solve this sample complexity problem and to generalize. And yeah, there are all sorts of interesting things to explore.
Thank you, Sheila. This was a very thoughtful and thought-provoking talk, and we hope that you'll come back in a couple of months to share some more state-of-the-art results and share some more experimental validation of your approach. But really appreciate the great work you've shared, your collaborators have shared, and we look forward to having you back soon. Thank you.
Well, thank you for the great questions, and thanks for having me.
Yes, bye for now.
Bye.